Okay, so we're going to discuss what's an open protocol, why DNP protocol is adopted, what's the DNP standard, what is the DNP stack, what are the levels of support in DNP, and then I'm going to discuss the D20 DNP implementation, and then we're going to show you an example of a DNP message. Then we will take a Q&A session. Now, for this first Q&A session, you can post your questions throughout the discussion of those first 7 topics. And after that, we will go into and show you how to configure a D20-MX DNP DPA configuration. And then we will do our second Q&A session, followed by a break for about 10 minutes. And then we'll show you how to do a DNP DCA configuration. And after that, we will have our final Q&A session. The overall time for this webinar is about 2 hours. Okay, so let's start with our first topic, which is the open protocol. Through the history of supervisory control and data acquisition, SCADA, many closed protocols were developed by professionals in the field of SCADA or control and automation. And these protocols were utilized in order to allow one device or one intelligent electronic device or IED to communicate with another intelligent electronic device. Soon it was found that one device has to act as a master, sometimes referred to as a client, right? And the other device has to act as a server or a slave device. The word master-slave has been dropped over the years, but it's still in use in some of the standards. So when we hear master or client, or we hear server or slave, it's the same. And the protocols that were developed by all the companies were basically closed protocols. By closed, it means it's not shared between one vendor and another vendor. Around the 1990s, there was a need to develop or come out with shared protocols. A protocol is basically all the semantics, the laws, the checks that take place on the messages that's exchanged between the 2 devices. So there was a lot of efforts in order to develop these protocols. For example, one of the good well-known efforts was written in the thesis of the Basic 4 document on the road to utility communication architecture, and basically started discussing how DNP protocol, which is shared among many companies, will be utilized. A leading company in the field of SCADA, part of GE, Wastronic, started to develop the GE DNP protocol. The first versions of the DNP protocol, version 1 and version 2, were not shared. Version 3, sometimes referred to as DNP3, between the year 1992 to 1994, started to materialize and get released. During the same time, there was other efforts to develop other open or shared protocols. For example, the IEEE UCA protocol, or Universal Communication Architecture, which was led by EPRI, was in development. The Electrical Power Research Institute was in development. And the IEC 6870-5, earlier known as 8870-5, was also in development. So, of course, because all of these protocols are in development at the same time and being discussed among professionals, they used to overlap in functionality or overlap in implementation. So we will see a lot of common features among these protocols, but at the end of the day, they're not the same. So DNP protocol is not the same as 870-5 protocol, okay? And it was an open protocol, a shared protocol that came out around the year 1993 with the first shared released protocol to all the vendors. With the shared protocol being available and many others, the question is why DNP? Why do we use DNP? DNP was developed as a result of all the knowledge that Westronic, or what used to be known as Westronic and today is GE, as a result of all their gathered knowledge in the world of SCADA and automation. So there is a lot of benefits that exist in DNP. Select before operate, broadcasting of messages, quality information that's constantly exchanged between the device and the master, or the device and the client, informing of all the different information about the device. Also came out with new ideas that weren't common in the closed protocols, for example, unsolicited messages. So an unsolicited messages, it means that before DNP, only that the master was always aware of what message is going to receive as a result of a polling that's sent by the master. An unsolicited message is what we call peer-to-peer communication, where a device will send information even though that information was not requested as a result of an event or a result of a change in data that the device has been programmed to report to the other device or to the master. So this opened the way for other open protocols to start implementing something similar to an unsolicited message. So all of these great features, time syncing, which wasn't a strict thing that's available in a lot of other devices, level of support, so devices could be at level 1 DNP or at level 2 DNP. And pay attention to this. DNP version 3, right, is referred to, sometimes the V is dropped, so we say DNP 3, and then the level of support of the device. So you have DNP 3-L1, that's DNP 3 device level 1, and DNP 3-L2, the DNP 3 level 2. And that means that the device has the ability not to include all the information or support all the codes in DNP, but can have smaller implementation of DNP. This made the protocol or the standard very flexible and widely adopted. And over the years, against all the criticism that was provided with the overhead and the checks and the type of message, DNP has proven to be very, very trusted, and comes with a high trust support from any implementer, and as such has gained a wide adoption among SCADA implementers or SCADA vendors. So now that we understand how this open protocol came to life, let's talk a little bit about the DNP protocol, distributed network protocol, and what have been produced over the years, and how did it evolve over the years to become what we have today, which is the 2012 IEEE standard released today. And probably it will keep on improving and evolving over many coming years. Okay, so over the years, the DNP 3 or version 3 protocol came out in 1990 to 1994 was the release of the protocol, and many items were resolved with the users via the DNP users group. who adopted the DNP protocol and started to service the users and the testing process. And then in the year 2010, Standard 1815 was released by the IEEE, and this was like the second formal release of the standard. And by the way, the image is not that far from reality. I mean, the standard is really very thick on release, but that's because I think it's very good. It does really handle everything from history to a very clear documentation of every message and what's the expectation of the message going from the master and the reply from the devices. Another release took place in the year 2012 and probably it will keep improving over the years. One thing to note is, regardless of how big the standard is, it cannot handle every situation available. So one of the common things that's in everybody's mind these days is security, right? And there is lots of criticism around DNP and DNP implementation, as far as it's easy to break the message or hack into the message and whatnot. But let's remember that when this protocol was created in 1990s, the security was not in everybody's mind. That what was in everybody's mind is to have this open, shared protocol that gains a great adoption. And even today, there is, depending on who you talk to in the industry, they might say UCA 61850 or IEC 6870-5 or DNP. So even today, the adoption is a little bit still not clear as to what's the best protocol. So the standard is great from covering all the communication and the parameters of communication and the security requirements, and I think it will keep improving for years to come. Just to gain a deeper understanding of the standard, why don't we take a look at the stack or the DNP stack and the contents, how is it built, how is the application laid out, and that maybe will help us understand more of the standards instead of just reading the 1,000 pages in the standard. Most of the protocols define the communication between one application and another application, or layers, what we call as layers, in the Open System Interconnection, or OSI. That made it easy for one application to focus on its task and make sure the task is done properly, and hands off the message to the next layer once the message is complete and ready to be transmitted. Now, the OSI has 7 layers, and the DNP group decided to use the EPA, or the Enhanced Performance Architecture. As you can see in the picture, the EPA has 3 layers. There is the application layer, the data link layer, and the physical layer. Each one of these layers can be broken further. For example, there's people out there that would tell you that the application layer has a layer above it, which is the user layer, or the link layer has a layer inside it, which is the transport layer. And that's true. There is other layers that will show up in DNP as communication requirements show up in the field of communication. But at the end of the day, the adopted layers by the DNP protocol was the EPA layers, right? And that's the application, the data link layer, and the physical layer. If we want to discuss some of the new layering that's taking place in the field of communication or the new stack, what you will find is inside the application layer, if you're complying to a level 4 device, you will find an extra functionality built into the application layer, or an extra layer if you like, which is the DNP Secure Authentication, DNP 3, or this is DNP version 3, Secure Authentication layer. Also, like I said, in the data link layer, you might find there is a DNP transport layer. So the new stack will look something like this: the application layer, including the secure authentication layer, and then a transport layer, and then a data link layer, and then a physical layer, which could be either a serial physical layer or an internet protocol suite layer. As we discussed, that the devices will have some of these layers, not all of these layers, and it all comes down to the implementation of DNP in that device. So to ease up the implementation of DNP in that device, we have talked earlier about levels of compliance to the standard, or levels of adoption in the standards of the messages that are available in the standard to be implemented by the device. The DNP3 protocol will keep on improving over the years. Many messages were developed in order to service the community of DNP users group needs. So, for example, today there is 147 messages available, and it covers everything from the basic communication of just give me a status of a point with no time reference, to authentication that this is a trusted device, it can send and receive messages. And that's about 147 messages to comply with from the master. So the master has to process any message that's part of these 147 messages to be transmitted and received. And what you will find is that this is the maximum, or the level 4 as of today. There will be probably new levels introduced in the future, and the simplest level was a level 1 device, and in a level 1 device the support was only for 36 basic messages, right? So the levels change. At the end of the day, let's not forget the aim of the protocol is to transfer data and information. The information is referred to as metadata, or information about the data. For example, what is the point online or offline? Does the point has a time tag with it or without a time tag? So all of this was required in order for full functionality of communication to be achieved between two intelligent electronic devices, one acting as a master, the other acting as a slave. One of the key things in communication in DNP is how do we refer to the data that's being generated, a voltage measurement, current measurement, a status of a breaker. All of this information that is available in our substations is basically translated into digital data, either a digital input or a digital output, an analog input or an analog output, a counter, or a status of a device. And this information is referred to with an index. So the data has an index. The breaker 1 is referred to, status is referred to as the DI1, right? Digital input 2 would refer to another status maybe of the same breaker or a different breaker. But what we end up with is a grid of information that basically points out an index to every piece of data or information in the field coming from the field is built into this grid of informations that is transmitted from the primary devices in the field to the secondary devices in the field to all the way until it reaches the control centers as information transmit over DNP. The data was not only put in indexes but also in groups classification. So let's say you want the critical data or the class 1 data, or you want the class 2 data, which is less critical, or you want the data that's just a measurement that doesn't impact your day-to-day transaction but is just to keep and make sure that the integrity of the system and the information required for your clients is available. So grouping was just a method of classifying or allocating the data generation. One thing that the protocol works on is object variation and quality. So any data that's generated should be placed inside an object. So it's just an encoded representation of the point. And that data could have many variations. So we could have 32-bit integer value with certain flags, or 16-bit integer value with a flag, or a 32-bit integer value without any supported flag. So the flags were information or metadata that would say whether the points are online or offline. So let's take an example. If I say the information from the field is showing that the breaker is open, right? Or status is the digital input value is 0. Is it 0 because it's really open? Or is it 0 because the monitoring point is offline? So that's why this extra data is important to us as monitors of the SCADA system to take the right action, that we're not just looking at the value of the data, but we're also looking at the status or the quality information of that data that we're receiving. Now that we understand the data that's being transmitted between two devices, what kind of messages can we transmit between the two devices? What's the classification of these messages? So in the standard, they say there is 3 types at this point. There's a confirmation message, a request, and a response. The confirmation message is a message that's sent between the master and the outstation, telling or informing the device in the field that the master has received the message, and this confirmation is sometimes handled at the data link layer, and it could be handled by other layers, but it can be turned off if the device does not require this confirmation message. This is a common thing for me in the classroom when students are looking at the messages between two devices and they see a lot of confirmation or enter messages between the pollings. And they go, well, how come there is an extra message in every polling? Well, that's because for every message, the master is sending a confirmation message. A request from the master to a server or a slave device could include either a read, a write, a freeze, or an immediate freeze, an authentication message, a file handling message like open a file, get a file, request, or a restart message. So the device is being requested to do a cold restart or a warm restart, or a clear of certain statuses, like a clear of a freeze status. The message is permitted by the standard as a reply from the device or the server to the master. Will have the value of either 129, which is a hex of 81, and that's basically just a response to a request by the master. Hex of 82 or 130 would be an unsolicited message, and that's a response without a request from the master if unsolicited is enabled, and the master has the ability to listen or ignore unsolicited messages. I get asked this question is, why would the master wants to ignore unsolicited messages? What if there is a device in the field that you can't service in the near future and it's just chattering unneeded unsolicited messages? Then you might want the master to just ignore the messages so that it's not raising false alarms, which is one of the annoyances that come with a SCADA system. And the last type of messages that could be responded is hex 83 or 131 decimal, and that basically is an authentication response that's part of the security buildup. Now, every message there is the I to N bits, or the internal indications bits, and those internal indication bits come is basically 2 octets, as you can see in the picture. Each bit in those 2 octets have a meaning. So it's either tell us that there is a class 1, 2, 3 data that's available for scanning, or it tells us that the device has received a broadcast message. And there is some important bits that will tell us that the device is occupying a trouble state, or the device receives an unknown object, which means an unsupported message, and or it has a buffer overflow. So those I2N messages are basically utilized by the master in order to manage what polling needs to happen to the device, or inform the person who's taking care of the system to dispatch the right engineer to take the right action at site with that device. And depending on the device, maybe the device require a restart. It might be handled remotely, or it might need to be handled physically at site. So these I2N bits were defined in the standard as an important part that will tell us about the device status and some quality information about the device. So we have a good understanding of the messages being transmitted between the master and the server or the slave device, and the type of objects. This brief understanding can be complemented by a reading of the standard if we want to get deeper into the protocol. In the meantime, I'll try to show you how the implementation of the D20 communication or the D20 platform of the DNP standard took place. So in the middle of the picture, we see the device, the remote terminal unit that's between the master station and the IED in the field. The remote terminal unit has the application architecture that will allow the storage of information until requested by the master station. Okay, so let's start the journey of information or data through DNP via DNP protocol from the IED all the way to the master. When an event takes place in the field, it's recorded by the IED, and that data change or event will be formulated in a DNP message based on the DNP standard, and then transmitted to the physical port connected to the IED. So now the message is at the physical port that's connected to the IED and is monitored by the physical application layer. In the case of the D2X platform, that will be either application B013 if the physical port is a serial port, or B052 if the physical port is a network port. Once the physical application integrity of the message is checked, it will take that message and pass it to the data link layer. In this case, the data link layer is application B015 or Bridgeman. The Bridgeman will check the source application ID or application address, that is the IED application address or DNP application address, and the destination application address, and the physical port through which this message should be transmitted. If the message meets all the data link requirements, the message is then formatted and transferred to the application layer that handles field devices. In this case, it's B023 or the DNP data collection application, which is DNP DCA. The DNP DCA basically picks the facts or the point status, the digital input 1 status, digital input 2 status, digital input 3 status, analog inputs, and store the information in the database, in the main database, or our WSDAC interface node or WIN database, application B008. The information will then travel to the application that is requesting the information, which is B021 or DNP data processing application. The DNP data processing application layer will format the message and send it to the data link layer, Bridgeman B015, which would check the integrity of the message, check where the message needs to go, and format the message, forward it to the physical application layer, which is B013. As you can see, as we're talking through the layers, the EPA layering is met from application to data link to physical layer. Now that the physical layer B013 has a fully well prepared message that can be placed on the physical port. What, depending, that physical port could be either a serial port or a network port. So once the message reaches the physical port, it travels over the physical media that's connected to the master station. The master station will process the information that's received from the D20 RTU and take the applicable actions, whether to show it to the operator who's monitoring the master station or to send a required programmed command. Okay. Hopefully this gives you an idea of the flow of information from the IED to the master through the RTU over the DNP protocol. Other applications can pick up the DNP protocol information from the WIN database or the B008 application or database that basically stores all of this information. So the information can be transferred either to a DNP master via the DNP application B021, or if there is a different master that is talking a different protocol, it can be transferred to that master also, as long as the data processing application that's servicing the other master is enabled and picks up the information from the WIN database. In order to get a good understanding of the messages and how do they get transmitted back and forth between the master and the IED via the D20, I've made a small capture of the communication between the D20 and an IED, and I'm just going to show you a deciphering of that message, basically a breakdown of that message. Okay, so I'm using a DNP translator, and basically I've captured the three messages, one from the master to the slave, and an acknowledgement from the slave to the master that the message has been received, and then the response from the slave to the master with the message. So let's start with the message from the master to the slave. The message is basically three layers. So you can see there is the data link layer, which is the top part of the message, and a DNP message always starts with 0564. As you can see in here, 0564. So that's a starting of a DNP message. The next thing that you will see is that the length of the message. So we can see 14 in hex or 20 in decimal, and that's the length of this message. After that comes the control part of this message, which is it tells us that the direction of this message is from the master to the outstation or to the secondary device. Okay, and some of the bits which can basically tell us about the controlling version and the function code that is being requested. Then we have the destination address, which is 50, the source address, which is 100, so 6400. That's the destination address and the source address. So this is a 20 length message, and it's from the master to the slave, and it has a destination address of 50 with a source address of 100. And then comes the cyclic redundancy check for, or the CRC for the header part. So in this case, it's saying that cyclic redundancy check is valid. On the transport layer, its only responsibility is to assemble more than one frames or multi-frames into a single frame. So in here it's saying this is the first frame and this is the final frame. So no additional frames are added to the device. And there is a counter for the message. The most important piece is the application layer. So this is in reverse of the stack that we discussed earlier, where you have the data link, the transport, and then the application layer. In the application layer, again, we start with a control, which basically tells us that this is the first fragment and the final fragment of a message. And the sender is not expecting confirmation, which is the master in this case, and we're sending a read request function code 1. All right, the user data, we can look at the translated data. So the translated data says this is a class 1, 2, 3, and a class 0, object 60 variation 1. So we are doing an integrity check, which means there is no range. Send me all the objects, all the points that is available in the target device. The next thing we see is a data link layer message. It has no application layer or a transport layer part. And basically the message size is, of course, it starts at 0564, and the message size is 5 bytes. And then we start with the control, which tells that this is from the master to the secondary station. right, from the master to the secondary. This is from the secondary station to the master in the direction of the master. And the destination address is 100, the source address is 50 with a valid CRC. Okay, then after that, we receive the answer from the device. And if we look at the translated values, as you can see, it only says 0.0 is 0, 0.1 is 0, 0.2 is 0. Now it's only sending the status of the points, okay? And it's sending the first point index number is 0, the second, the last index number is 2. One thing to note here, the naming of the points doesn't get transmitted with the message. So you have to make sure that the name or the tag name is the same name or is what your operator is expecting to see in the point display in both the master and the server device. Okay, so hopefully this gave you a good understanding of what goes on between the master and the device with an acknowledgement, which is constantly repeating in a substation based on a polling duration that you pre-configure in your substation. Okay, so to recap, we have covered the DNP protocol, its history, how the stack is laid out of the applications, get you familiar with the applications that are available and how the messages compare to an OSI layer message. And finally, we've shown you a breakdown of a DNP message. Again, it starts with 0564, and then you got the destination address, the source address, the function codes, all built into this message. One message that comes from 3 layers back and forth between the master and the device or the slave device. Thank you for your questions. We'll start with the first one. How many type of polling is supported by the GE equipment? The GE equipment will support all type of polling. Level 3 is the current supported one. As I mentioned, there is a security level coming up, and GE is also coping up with the changes. So once the security definition is in place by the DNP committee, GE equipment will also comply to the GE security messages. What kind of polling is available in a level 3? Well, there is basically 24 polls that are available right now between class 1, 2, 3, an integrity poll, and the rest of them are binary digital input polling, and the different flags for each one. The last question is, what's a qualifier? And if I can give an example, a qualifier basically in a message is the number of points that's required or a certain criteria about the data that's required. For example, you can say I want it with time or without time, or how many points do we need, and that's sometimes gets mingled with a variation. For example, qualifier number 6, it means give me all points that are available instead of specifying a starting and an ending point in a poll of a message. Okay, thank you. Okay, so for this lab, this is a view of how the lab looks like. Basically, we start at the peripheral link. The peripheral, which is the S board, is connected using your straight-through cable to the D.20 port or D.20 peripheral link port on the D20 on the back of the chassis. And then the application that we will enable for that is going to be B003. So we'll enable application B003 and B008 and B014 and B021, B015 and B013. Eventually there will be a DNP master polling this RTU. In the B003, all we're going to do is we're going to tag 3 points, which is point 3, 4, and 5, with the first DPA point, second DPA point, and third DPA point. Then these points will be in the Win database available for the DPA to pick them. We'll put the address of the DPA as 50 and the master address as 100. And now that we know that the address of the DPA is 50, the master address is 100, next we will map these 3 points into the DPA, and we'll configure Bridgeman local application table and remote application table on the Bridgeman. Both these tables will just bridge the local application address 50 to the B013 and the remote application address 100 through B013. In the B013 itself, we were just going to configure one record, which is B013.0. Be careful with this. This is very confusing. It's not B013.2 because we're configuring COM2 on B013. So B013 is going to talk through the serial port COM2 on the back of the D20, which is labeled as SIO2, and that record will be labeled as B013.0. So in Bridgeman, when we configure that, it's going to be B013.0 connected to local application 50, and B013.0 is connected to remote application DNP application 100. Okay, so let's get to it. We will basically show you a basic configuration of DNP DPA. As we said in the picture, we'll have the points mapped into the DNP DPA. Follow it slowly, try to understand each step and why we're doing each step, and keep referring back to the picture that we have. The first step is to create a project, so we click on the G logo, new project. DNP DPA. And then we click OK. Now our project is available. We can see the navigator, the reference document, and the device templates available. So we're going to click on the device templates. We'll open the tree for D20MX. Go to our latest D20MX, just put a new installation in here. And our device is created and ready for configuration. While highlighting the device, we put the name. So this is going to be DNP DPA or server. Okay, we're not going to make it a LAN based, as we're going to make it just a serial DNP, and then we click next. And we have the part number defined, we have the firmware defined. If we're happy with that, then we just click next and click finish. Now our device is ready for configuration. Double click on the device and we open the device setup. We're gonna disable the Internet Protocol stack, and we're going to enable 5 applications. So I'm gonna show disabled applications. We're going to enable the B021. And we're going to enable the B013. And the B015. So if I go back into my list of applications, we've got the peripheral link, We don't need the IRIC-B. This is only a lab setup where the IRIC-B is not part of the RTU. If you're setting this in a substation, you probably need the IRIC-B. But in this case, we've got the D.20 peripheral link, the DNP DPA. I'm going to disable the LAN manager. So finally, you should end up with those 6 applications: B003, B021, B008, B014, B015, and B013. So that's the first step, is to enable the right set of applications in order to create this server. So we will start with the D20 peripheral link. Depending on the peripheral that you have for your lab, you just select your peripheral. In this case, I have an S. You could have a C0 or a C1 or a C2. So I'm just going to put my S board and click OK on that. And when prompted for the naming, I'm going to pick point number 3 as first DPA point. And point number 4 as second DPA point. And point number 5 as third DPA point. So I've got those 3 points which I would like to map to my DNP DPA. And that's it. My peripheral link is set up. Once you set up your peripheral link and your peripheral is available in B003, you can hover over the peripheral and you should get a tooltip. Basically, or even if you open the peripheral, there is an address that is hex3, and the address tells you that the jumpers need to be set up as the first jumper need to be shorted, the second jumper need to be shorted, and then the rest of the jumpers need to be unshorted. Okay, that's the bank of address of jumpers on the peripheral. So from left to right, basically is top to bottom, or sorry, your right to left. 110000 will be your top to bottom. So from right to left is your top to bottom on the jumper settings. Wherever you see a 1 is shorted, wherever you see a 0, it's not shorted, right? And that's it. Our peripheral link B003 application is set up. That's all you need to do in the B003 application. You can start to use your navigator to go through the applications. So the first one is B003, and we are done with that application. The next application that we will set up is the DNP DPA. So now that the points are in the Win database, or B008, we will go to the DNP DPA and go to the binary input map table. Select the points that we want. So we selected the 3 points that we need to map to the B021. And then we go to the DPA configuration. We put the DPA address as 50, the master address as 100, and we go to the DPA points. Select the first binary input point, highlight the 3 points, and that's it. The job is done. So basically you have mapped the first DPA point, second DPA point, third DPA point, which is coming from B003 into the binary input points that is mapped to address, master address 100 from master address 50. And then we click OK, and that's it. The mapping is done. And that's all you need to do for your DNP DPA configuration. we save our configuration. The next application we need to configure is the DNP Datalink B013. In here, you want to configure the port, so we will leave it as COM2, which is B013.0. So remember, B013.0 is basically this record. When we go to Bridgeman, we're going to map B013.0 as this record. And that's it as far as configuring B013. And we go to Bridgeman. We configure the local application table. So the local application is 50, B013.0, and the hex of 50 is 16. Sorry, 32. And then we go to the remote application table. We put the address 100 B013.0 and the hex of 100 is 64. Now my Bridgeman is configured. Just to summarize, we configured the peripheral link, the Bridgeman, the B013, and the DNP DPA. Our configuration is ready for download, so we close, generate our configuration, there was no errors. Now our device is ready for the download, so we can connect to our device. We set up the options of connection. In this case, it's going to be direct serial, and we will connect to COM6. We enable the fast download baud rate. Then we click OK and click connect to our device and download the configuration. Now that our configuration is ready, we're going to download it and then show you in the terminal how to see that the application is up and running. Okay, so we connect to the device, type in the name and password. We go to the shell option and we download. So the first step is going to change the baud rate, then clear the NVRAM, then start the download at a higher baud rate. Then it's going to reboot the system. So we click on boot. And we log in. We go to the system function, check the error log. We don't have any special errors. All it's saying that IRIC-B is not enabled because we, like I said earlier, we are in a lab environment. IRIC-B will not be enabled, and radius is not configured for this device. So these are information that's acceptable. And the other thing that you can do is to do a query process, and you will find that all your applications are in pending or not suspended status. So IRIC-B in suspended status. B021 on the other hand is in pending status or running status. So now we are done configuring the DNP DPA with the 3 points that were mapped from B003. Okay, so just to recap, we basically configured application B003. We put 3 points in it, and then we mapped the points from the Win database into the B021. We put an address 50 local, 100 remote for the master address, and then we went into B015. We mapped the local address 50 in the local application table to the COM port B013.0, which is COM number 2, and then we mapped the remote address 100 to through B013.0, which is COM number 2 also. Then we went into B013, even though the default is set up to COM number 2, but we could have set up to any default to any other COM port if required, and that was it. This is basically how you configure the DNP as a slave device or as a server to the master. Thank you for your questions. So the question is, what kind of master the DNP DPA will reply to? Any DNP master that's compliant with the level of the DNP DPA. In our case, the DNP DPA is currently compliant to level 3, which is the B021 application. Okay, what's the point type that's supported by the B021? All point types that is currently defined in the standard is supported by the DNP DPA. And will the DNP DPA reply to a staggered request? And the answer is yes. The staggered request is normally initiated by the master to all devices, and the DPA in turn will reply to the master once requested for the points. Okay, and when do we set up the buffer in the Bridgeman? Basically, when you have more than one link, like if there is 3 or 4 links, that's when you have to set up the buffer in Bridgeman. The buffer by default is set up to 3, so it's the number of links plus 1 if you read the configuration guide. So let's say you have 3 connections, then you would need 4 buffers. Okay, hopefully that answers all your questions for the DNP DPA. So at this point, our IED with address 50 and 3 digital inputs is set up and ready to report. Okay, we're going to connect it to physical COM port 3. And for this lab, we're going to set up the DNP DCA as an address 100. It's going to communicate, of course, we're going to configure the local application table and the remote application table similar to the previous setup. And the points are going to go into the Win database. In the Win database, the points will be populated along with the pseudo points. Right, so let's get to it. The steps of the configuration first include the enabling of the applicable applications and then configuring each one of these applications. Okay, so the first step is to create a new project. Gonna name it lab _405 _ DNP DCA. Then we click OK. Now that we have an empty page, we can go to device templates, grab the new installation under 1.6 or whatever is the latest MX or the MX that you have version. And then we give it a name, my DNP master. We're going to uncheck the LAN-based. And if we're happy with the part number of the board and we're happy with the part number of the firmware, we just click finish on the next interface. Okay, so we click next and finish. Now our device is available. We need to disable all the unneeded applications, so we'll disable the peripheral link. And we'll disable the IRIC-B. And we'll disable the LAN manager. Also, we'll disable the protocol stack. Now we need to enable our target applications, which is B023. B015. And B013. If I uncheck the show disabled applications, we should end up with B023, B008, B014, B015, and B013. So I click close. We start our configuration with the B023. In here, you can start with the DCA. The DCA address is 100. And this master record will show up as the first record in your Win database. So that's what this index is all about. Now notice every time you go to one of these fields, you get a little tooltip at the bottom that explains what this field is for. And then we go to the first device entry column. In the first device, we put the device address. In this case, it's 50. And we go to the device configuration table. So we want to make sure this device configuration table is very big to configure it. And then go to the first point record and set it to 3 binary inputs. That's what we're bringing in. Make sure the range is selected. Click OK. And the first poll record, we'll set it to integrity poll. And then click OK on that. Click OK on that. And make sure your record is selected, and that's it. Your B023 is configured. Next, we're going to configure B013. We're going to go into the port configuration table, set it to COM number 3, make sure everything else is set to the default, save it, close it. You're done configuring B013. Next, we'll configure B015. Local application table, the address is 100 B013.064. Okay, so we have finished configuring the local application table. Now we'll configure the remote application table 50 B013.0 and 32. Okay, so we have finished B023 configuration, B015, B013. Now you need to configure B008. In order to configure B008, you would have to set the number of points that is required for the 3 digital input points, and then you have to set up the descriptors once you set up the points. In order to do that, you would need to refer to your manual and go to the B023 configuration guide and go to the pseudo points and go to the pseudo point summary, and you will find the points. So we need 3 global points, and then you put your physical points, and then you put your per device points, and then you put, for the digital outputs, you put your global points and your digital outputs, and then your per device points. And for the analogs, you put your physical, there is no global points, and you put your per device points. In the next step, we're going to show you how to configure the WIN database. Now, if you're in a classroom environment, you have access to the Excel sheet that's shared with as a student tool. Otherwise, you use the document, the PDF document, which can be exported inside sgconfig from the exported documents. At this point, we want to configure the B008. One way is to read the manual and get to the pseudo points. The other way is to use the Excel sheet that's provided in the classroom as part of the student tools. So in the Excel sheet, I'm just going to summarize the information. You really don't need to do these steps. You can just simply enable the device, and you put the device name, let's say DNP device from S-board. Depending on the board type, if you have a C board, then you would say from C board. And then you put the DNP address, which is 50. You put a prefix, let's say D20 MX. And then you put a suffix, let's say pseudo point. Okay, we can decide on the polling grade that we put, which is an integrity poll, all points from 0.0 to 0.3 with 5,000 seconds. Okay, and then we can put the names of our points. So we named our points DNP DPA point 1. And we use the power of Excel to populate the points quickly. So now we've got our points. Now we can generate the descriptors, and we have the point count. So 22, 19, 5, and 1 device. We go back into sgconfig, and we go to the WIN database, open the instance, 22, 19, 5, and 1, and that has been calculated easily for us in the Excel sheet. And to generate the descriptors, we can go generate the descriptors, decide where we want to place those descriptors, let's say in the desktop, and I want to create a new folder. I will name it my descriptors. Okay, and I'll go to my descriptors and just select that this is the path where I would like to put all of these descriptions. And just to show you, basically all the descriptors are created. So if I open the DI descriptors text, it has the D20MX, device globally disabled, pseudo point, and it has all the descriptions in here. So we can import these descriptions directly into the sgconfig. So if I close this one, go back into my sgconfig, go to descriptors, and then I say import all points, and I click OK. It asks me where I want to import them from. Remember, we put them in my descriptors, so we just highlight my descriptors, click OK, and all my descriptions for the digital input points are here, for the digital output points are here, and for the device name is in here, the descriptor name in here. As you can see, there is a maximum. The reason I wanted to put this pseudo point at the end is to show you that it will get truncated by sgconfig due to the maximum naming constraint. So make sure you don't exceed that maximum naming constraint. Now let's say we want to fix it, right? Because now this naming is very big, it's going beyond. So we can go back to the Excel sheet, remove the suffix, take out the extra space after the MX, and we can generate those files again, and we'll put them into the same directory. And we'll click OK. Now the files have been regenerated. As you can see, there is no pseudo points at the end of it, and I can import them again into my sgconfig. So we click OK, go to descriptors, and we can click import all points, click OK, select the folder again, and click OK, and now we can see that all the points have been imported. Okay, now these points are named from the data sheet in the Excel sheet. So let's say you go to the data sheet and there is a naming that you don't like. For example, this digital input is going beyond what's allowed due to the addition of the prefix of the D20MX. And so it's going beyond a little, and you just want to drop the word globally in here, or drop the word responses for unsolicited. That's very easy. You just go into the Excel sheet, fix it, and click save. You can generate again, go to the desktop. I'm just trying to show you how to use this tool to ease up the generation of the point descriptors. And now I can import all points, click OK, and select my descriptors, click OK. As you can see, this is also fixed. So as you can see, it's easy to generate the pseudo points and populate them inside sgconfig, and your configuration for the D20MX DNP DCA master is ready for generation. So we highlight the device and we click generate. 0 errors and 0 warnings. So our device is ready for download of configuration. So we'll show you that next, and we'll show you how to look at the communication with the device. Okay, so with my device highlighted, I click on options, make sure that we select the right COM port, make sure the port setting is set up. We can enable the fast baud rate download. We connect to the device, and when you connect to the device, double check that you have the right title on your terminal. All right, so we press enter. We make sure we're connected to the master device, type in the admin and change me, and this device has no issues. We can download our configuration. Just press F7. It will change the baud rate to a higher baud rate. Clear the NVRAM, and our download will start at 115,200, as you can see. Once the download is done, we will shift back to the 9600. So it's asking me to reboot, so I'm going to reboot the device. Okay, ready to log in. We log in. Now we go to the error log. Make sure there is no extra errors, just like in the DPA. And we can go to the device status display, and we can see that there is 8 transactions, no retries, no failures. The device is online. We can go to the shell, and we can SA the COM port. So if you remember, on the master it's COM3, so we'll SA COM3. And we can see that there is polling taking place. If we want to decipher this polling, we can disconnect and start our DNP translator. You got it as part of your tools in the classroom. Okay, all we need to do is just highlight the messages, right click, copy, go to the DNP translator, paste, translate, and we can see there is a read request from the master with a response from the device, and another read request and a response, and every one of these you can open it up to see the full message. So we can see that this is from the master to the device. That's basically all of these bits. And you can see that this is an integrity check basically that is sent, and the response from the device, again with all the bits, and you can see that the points, 0.0 status is 0, 0.1 status is 0, 0.2 status is 0. Okay, so we can see that there is valid communication being transmitted between the master and the slave device. You can further use this in order to learn more about the DNP protocol and the parameters through the messages of the standard. And you can save your messages if you want to share it, or you can at this point close, and your lab is done. So just to recap, basically what we've done is we've shown you how to configure DNP DCA. It's very simple. All you need to do is make sure you have the picture clear in your head as to what you're trying to configure, what addresses you're trying to put in. Once that picture is clear, the mechanical work is basically you configure the B023, then configure B013, B015, and finally don't forget to place the points in the Win database. The common pitfall is people forget to populate the devices number as the number of devices that are connected, because they're very busy with the pseudo points of the digital inputs, digital outputs, and analog inputs. Once that's done, you generate your configuration, download it, and you can view your communication with the devices exchanged back and forth. Okay, thank you for your questions. So this is the final Q&A session. So some of the questions were generic, some of them were very specific, so I'll start with the generic ones. Do we really need to configure the pseudo points if we're not using them? And the answer is yes. You will need to configure them anyway. And as you've seen, the tool that I created was a very simple tool that create those pseudo points, and when you come to the lab, you get it. But if you don't have it, I mean, it's very easy to develop. So once you develop, and I've seen many companies develop their own pseudo point generation application. Okay, very good question. Next question. Right, does the DCA support concurrent and staggered polling? And the answer is yes. So the difference between concurrent and staggered is concurrent, you send it to all the devices, you receive a reply from all the devices at the same time, versus staggered, where you send to one device, wait for a reply, send to the next device, wait for a reply, and so on. Okay. The next question is, does the application support 32 analog input, and what variation? And the answer is yes, it supports 32 analog input with flag, without flag, 32 analog input event with time pole, or without time pole. Now, because I'm saying 32 put analog inputs, just remember that it will store it in 2 points in the Win database. So it will use 2 analog input points to store one 32-bit value that's received from the device. And then when it's reported to the master, it will be reported in 2 points to the master. And another question that is a good question that just came up is, can it support signed and unsigned? And the answer is yes, it will support signed and unsigned, but kindly notice that when it is displaying it in Westmate, not at the master, it will display the value as signed, because all the values are being displayed as signed. When the master will get it as unsigned if it is stored in as unsigned. I mean, it's just a matter of that 16th bit being interpreted by the master as signed or unsigned versus being interpreted by the terminal as signed. Okay, right. This is a question that's a little bit outside of what I've discussed, but it's close enough. So it has to do with network on the DNP. Network is supported on DNP DCA. As I said, B052 has to be configured. And the question is, what do we look for? You just got to make sure that your host name is defined properly and that you make sure an ISCS generation is done, not just a normal generate, but a full generate, because that will populate the B100 table. So that's a common thing that happens when you go for networking versus serial configuration. Okay, a generic one. Generic question is, am I gonna show you how to do DNP networking in the future? Sure, I hope I'll put on some webinars on DNP networking. Great. Well, great. Thank you for the participations and the questions. Just to summarize, what we have covered in this webinar is that the DNP has a wide adoption among vendors. This wide adoption was due to the way it was architected by GE, with the EPA stack being very efficient for every application layer to basically process the next application layer message. And the DNP level allowed the flexibility for different vendors to implement a portion of the protocol and not be stringent to implement the entire protocol. So from DNP level 1, 2, 3, and 4. And the messages that were implemented were basically pertaining to each one of the stack layers. So you've got the data link layer, the physical layer, and the application layer part of the message. And then we showed you how each message starts with the 0564, and then the breakdown of these messages where it shows the direction, whether it's from the master to the slave to master, is it the final message, is there more fragments of it, and the object and variation in each message. So one big part of understanding DNP is to try to understand how to look at these messages and try to break down these messages into meaningful syntaxes. And the DPA configuration, don't forget to enable the B021 application and B013, B015, which is the Bridgeman between the B021 and the physical layer, which is B013. For the DCA configuration, you want to enable the B023 application. And again, you want to enable the Bridgeman, which acts as a bridge between B023 and B013 in the case of a serial communication. Thank you for being with me in this webinar, and I hope to see you in future webinars.